Subscribe to the channel so you don't miss out on any of these videos. The sun might look like a fiery ball that sits in the sky, heating and lighting our planet. But what if I told you it's constantly sending out an invisible force, spiraling through space like a cosmic web? And what if that invisible force is the very reason the solar system dances in harmony? This isn't some sci-fi plot, this is the Parker Spiral, a real phenomenon shaping the solar wind, bending magnetic fields, and stretching the sun's influence across billions of miles. Stick around, because by the time this is over, you'll never look at the sun, or the space around it, the same way again. Let's get one thing straight. The sun isn't just sitting there, passive and peaceful. It's alive in every sense that a star can be. At its core, nuclear fusion creates enough energy to power our solar system, but there's so much more happening beneath its surface. The sun is a swirling, rotating sphere of plasma, and this movement generates a colossal magnetic field. But what happens when you take a spinning magnetic field and let it interact with a constant stream of charged particles? You get the Parker Spiral, a phenomenon that not only redefines how we think about the sun's power but also explains the strange, intricate structure of the solar wind. Here's where it gets wild. The sun doesn't release its energy in a straight line, even though it might seem like it would. You'd think the solar wind, those charged particles streaming out from the sun, would just shoot outward like water from a hose. But the sun is rotating, and this rotation creates a kind of magnetic whirlpool. Imagine spinning a garden sprinkler while water sprays out of it. The streams of water wouldn't go straight, they'd spiral outward in a curve. That's essentially what's happening with the sun and its magnetic field, except the scale is unimaginably larger, and the forces involved are cosmic in scope. The magnetic field lines coming from the sun are carried outward by the solar wind. But because the sun is spinning, those magnetic lines get twisted into a spiral shape as they move away. This is the Parker Spiral, named after Eugene Parker, the astrophysicist who first theorized it back in the 1950s. At the time, the idea of the solar wind wasn't even widely accepted. Many thought space was a void, static and empty. Parker's work not only proved the solar wind existed but also showed that it wasn't random, it was structured. Now let's talk scale. The Parker Spiral isn't some small, localized phenomenon. It extends well beyond the orbit of Pluto, stretching into interstellar space. Think about that for a moment. The sun's magnetic influence reaches so far that even at the edges of the solar system, spacecraft like Voyager 1 are still feeling its effects. And yet, it's not static. The Parker Spiral is constantly shifting, responding to changes in the sun's activity. When the sun releases a burst of energy during a solar flare or a coronal mass ejection, that energy travels along the spiral, causing ripples that can impact planets, even Earth. This brings us to a fascinating point. The Parker Spiral isn't just an abstract shape, it has real, tangible effects on our planet. Every time you hear about a geomagnetic storm or a disruption to satellites and power grids, you're witnessing the Parker Spiral in action. Those charged particles travel along the spiral, interacting with Earth's magnetic field and creating auroras in the sky. But these same particles can also wreak havoc on technology, which is why understanding the Parker Spiral is so crucial. But the story doesn't stop there. Scientists are still uncovering new details about how the Parker Spiral works. For instance, the strength and shape of the spiral can change depending on the sun's 11-year solar cycle. During periods of high solar activity, the spiral becomes more chaotic, with stronger bursts of energy being sent outward. During quieter periods, it's more stable and predictable. This dynamic nature makes it both fascinating and challenging to study. Speaking of challenges, one of the most groundbreaking missions to study the Parker Spiral is the Parker Solar Probe. Launched by NASA, this spacecraft is designed to get closer to the sun than any probe before it. Its mission? To dive into the solar corona, the sun's outer atmosphere, and gather data about the solar wind and magnetic fields. The Parker Solar Probe is already giving us unprecedented insights into how the Parker Spiral forms and evolves, helping us piece together the puzzle of how the sun influences the solar system. Another intriguing aspect of the Parker Spiral is how it interacts with other stars and their magnetic fields. Our solar system doesn't exist in isolation. It's part of the Milky Way galaxy, which is filled with other stars, each with their own magnetic fields and stellar winds. As the Sun's magnetic influence extends outward, it eventually collides with these interstellar forces. The boundary where the solar wind meets the interstellar medium is known as the heliopause, and it's shaped, in part, by the Parker spiral. Understanding this interaction could help us learn more about how stars and their environments coexist, not just in our galaxy but across the universe. The Parker spiral also raises some profound questions. For instance, could this spiraling magnetic field have played a role in the formation of the solar system? Some scientists believe that the Sun's magnetic field may have helped shape the early protoplanetary disk, influencing how planets formed and where they ended up. If that's true, then the Parker spiral isn't just a current phenomenon, it's a relic of the solar system's birth, a reminder of the Sun's role as both creator and sustainer. And here's another mind-bender: the Parker spiral might not be unique to the Sun. Other stars, especially those similar to our Sun, likely have their own versions of the Parker spiral. By studying our own star, we could unlock secrets about other stellar systems, giving us a deeper understanding of how magnetic fields shape the universe. The more we learn about the Parker spiral, the more it becomes clear that this isn't just a quirk of the Sun, it's a fundamental aspect of how stars interact with their surroundings. It's a reminder that even something as seemingly simple as the Sun's magnetic field can have far-reaching, complex effects. The Parker spiral isn't just a scientific curiosity, it's a key to understanding our place in the cosmos. The Parker spiral connects us to the Sun in ways that are as awe-inspiring as they are consequential. It's not just a scientific concept, it's a bridge between our understanding of Earth and the vast mechanics of space. But the deeper you dive into its complexities, the more questions arise. For instance, how do subtle changes in the Parker spiral ripple across the solar system, influencing planetary atmospheres, magnetic fields, and even the potential for life on other planets? To answer that, let's break down the interplay between the solar wind, magnetic fields, and the Parker spiral itself. The solar wind, the driving force behind the Parker spiral, is a stream of charged particles released from the Sun's corona. It's not uniform, it varies in speed, density, and composition. Faster solar wind streams, often originating from coronal holes, interact with slower ones, creating regions of turbulence and compression. These interactions are like shockwaves traveling through the Parker spiral, adding layers of complexity to its structure. These shockwaves can even reach Earth, where they create geomagnetic storms. But why does the solar wind behave this way? It ties back to the Sun's rotating magnetic field and its dynamic, ever-changing nature. The Sun doesn't rotate as a solid object, it spins faster at its equator than at its poles, a phenomenon known as differential rotation. This uneven spinning twists the magnetic field lines, stretching and bending them outward as they are carried by the solar wind. Imagine stretching a slinky while spinning it. It doesn't just stretch straight, it forms a spiral. This twisting is amplified by the Sun's constant movement, and its changing magnetic polarity during the solar cycle. Over time, this creates a spiral pattern that extends far beyond the solar system. What's fascinating is that the Parker spiral isn't a rigid structure. It's dynamic, constantly reshaping itself as the Sun rotates, ejects energy, and interacts with its surroundings. Think of it as a living, breathing entity that mirrors the Sun's behavior. When the Sun experiences solar maximum, the peak of its activity during the 11-year solar cycle, the Parker spiral becomes more chaotic. Increased solar flares and coronal mass ejections send powerful waves of energy rippling through the spiral, creating disturbances that can travel for millions of miles. These disturbances aren't just theoretical, they have real, measurable effects on Earth. One of the most noticeable effects of the Parker spiral on Earth is the aurora borealis, or northern lights. When charged particles from the solar wind reach Earth, they interact with our planet's magnetic field, funneling down toward the poles. There, they collide with particles in Earth's atmosphere, releasing energy in the form of light. The result? Stunning displays of green, purple, and red dancing across the night sky. But these same particles can also disrupt communication systems, satellites, and even power grids. This is why scientists closely monitor the Parker spiral. It's not just about understanding the sun, it's about protecting our modern way of life. The Parker spiral's influence extends far beyond Earth. It shapes the entire heliosphere, the bubble-like region of space dominated by the sun's magnetic field. This heliosphere acts as a shield, protecting the solar system from high-energy cosmic rays that come from outside our galaxy. But the heliosphere isn't a perfect barrier. The Parker spiral, with its spiral-shaped magnetic field lines, helps direct and deflect some of these cosmic rays, creating a complex interplay between forces that we're only beginning to understand. This brings us to the outermost reaches of the solar system, where the Parker spiral meets the interstellar medium. Here, the solar wind slows down and eventually stops, marking the edge of the heliosphere. This boundary, known as the termination shock, is where the solar wind's influence wanes, and the sun's magnetic field begins to fade. Beyond this lies the heliopause, where interstellar space begins. The Parker spiral's structure influences this boundary, shaping how the solar system interacts with the rest of the galaxy. Understanding this interaction could unlock secrets about how stars and their surrounding environments coexist. And then there's the question of how the Parker spiral might influence other planets. Take Mars, for example. Unlike Earth, Mars doesn't have a strong global magnetic field to protect it from the solar wind. As a result, the Parker spiral's magnetic fields can directly interact with the Martian atmosphere, stripping away particles and contributing to the planet's loss of atmosphere over time. This process has significant implications for our understanding of planetary habitability and the potential for life elsewhere in the solar system. Even more intriguing is how the Parker spiral might affect the search for extraterrestrial life. The spiral's magnetic fields and the solar wind could impact the habitability of moons like Europa and Enceladus, which have subsurface oceans beneath their icy crusts. By studying how the Parker spiral interacts with these distant worlds, scientists can gain insights into whether these environments might support life. The Parker spiral isn't just a local phenomenon, it's a window into the universal principles that govern stars and their surroundings. Other stars, especially those with strong magnetic fields and fast stellar winds, likely generate their own versions of the Parker spiral. By studying our Sun, we can begin to understand these distant stars and their influence on exoplanets. This knowledge could revolutionize our understanding of how planets form, evolve, and sustain life. The Parker Solar Probe has been instrumental in uncovering these mysteries. As it travels closer to the Sun than any spacecraft before it, it's providing unprecedented data on the solar wind, magnetic fields, and the Parker spiral. These insights are helping scientists refine their models and uncover new details about the Sun's behavior. For instance, the probe has revealed that the solar wind is more dynamic and variable than previously thought, with sudden bursts and reversals in magnetic polarity that challenge existing theories. But there's still so much we don't know. For example, how do the Sun's internal dynamics, its convection currents, magnetic cycles, and plasma flows, affect the Parker spiral? What role do these processes play in shaping the solar wind and its interactions with planets, moons, and the interstellar medium? And could the Parker spiral hold clues about the Sun's past, including how it influenced the early solar system and the conditions that led to the emergence of life on Earth? These unanswered questions are at the forefront of solar and space physics, making the Parker spiral not just a phenomenon to study but a puzzle that intertwines with nearly every aspect of the solar system's behavior. Understanding the Parker spiral isn't just about solving one scientific curiosity. It's about piecing together how the Sun, its planets, and the vast expanse of space around us operate as one interconnected system. Let's dig deeper into how the Sun's internal dynamics influence the Parker spiral. At the heart of the Sun lies a massive nuclear fusion reactor, where hydrogen atoms combine to form helium, releasing enormous amounts of energy. This energy moves outward through the Sun's layers, eventually reaching the photosphere, where it radiates into space as light and heat. But beneath the surface, the Sun's convective zone is a boiling sea of plasma, with superheated material constantly rising and falling. These motions generate electric currents, which, in turn, create magnetic fields through a process known as the solar dynamo. This dynamo effect is central to the Sun's magnetic activity, and by extension, to the Parker spiral. As magnetic fields are twisted and carried outward by the solar wind, they form the spiral pattern we observe. However, the complexity doesn't stop there. The Sun's magnetic field flips polarity approximately every 11 years during the solar cycle. This reversal adds another layer of complexity to the Parker spiral, as it means that the orientation of the spiral's magnetic field changes over time. During these flips, the Sun's magnetic field becomes particularly chaotic, with multiple poles appearing and disappearing before a new configuration is established. This chaotic period has significant consequences for the solar wind and the Parker spiral. The changing magnetic field can create turbulence and irregularities in the solar wind, which ripple outward through the spiral. These disturbances can affect everything from Earth's magnetosphere to the behavior of cosmic rays entering the solar system. For scientists, this turbulence offers a unique opportunity to study the dynamics of plasma and magnetic fields under extreme conditions, providing insights that could be applied to other astrophysical phenomena, such as black holes and neutron stars. On Earth, we experience the effects of these changes in the Parker spiral as geomagnetic storms. When disturbances in the solar wind reach Earth, they can compress our planet's magnetosphere, creating temporary disruptions in its protective shield. These disruptions can lead to spectacular auroras, but they can also pose risks to technology and infrastructure. For instance, geomagnetic storms have been known to disable satellites, interfere with GPS signals, and even cause power outages. The most severe storms could potentially have devastating impacts on modern technology, making it critical to understand and predict the behavior of the Parker spiral. Beyond Earth, the Parker spiral shapes the space weather environment across the entire solar system. For spacecraft traveling through space, understanding the spiral is crucial for navigation and safety. The magnetic fields and charged particles that make up the spiral can pose serious risks to spacecraft electronics and the health of astronauts. Missions to Mars, for example, must account for the increased radiation exposure that occurs during periods of heightened solar activity. By studying the Parker spiral, scientists can develop better models to predict these conditions, helping to ensure the success of future space exploration. The Parker spiral also provides valuable insights into the early history of the solar system. When the Sun was young, its magnetic field was much stronger, and its rotation was faster. This would have created a more tightly wound Parker spiral, with a more intense solar wind. These conditions likely played a significant role in shaping the atmospheres and magnetic fields of the early planets. For instance, the loss of Mars's atmosphere may have been accelerated by the young Sun's intense solar wind, leaving the planet with the barren landscape we see today. Similarly, the Parker spiral may have influenced the formation of Earth's magnetosphere, a critical factor in the development of life. Looking beyond the solar system, the principles behind the Parker spiral can be applied to other stars and their planetary systems. Most stars generate magnetic fields and emit stellar winds, which means they likely produce their own versions of the Parker spiral. By studying these stellar spirals, we can gain insights into the environments of distant exoplanets and their potential habitability. For example, a star with a highly active magnetic field and a strong stellar wind might create harsh space weather conditions, making it less likely for life to develop on nearby planets. The study of the Parker spiral also intersects with broader questions about the nature of space and time. For instance, the spiral's structure is influenced by the interplay between magnetic fields and relativistic effects, such as the way the Sun's rotation affects the propagation of the solar wind. Understanding these interactions could provide new insights into the fundamental laws of physics, particularly in extreme environments where traditional theories begin to break down. One of the most intriguing aspects of the Parker spiral is its role as a cosmic messenger. The magnetic fields and charged particles that make up the spiral carry information about the Sun's activity and its interaction with the rest of the galaxy. By studying the composition and behavior of the solar wind, scientists can learn not only about the Sun but also about the interstellar medium through which the solar system travels. This information is critical for understanding how stars and their environments evolve over time. The Parker spiral is more than a pattern, it's a dynamic, evolving system that encapsulates the essence of the Sun's influence on the solar system. Its study requires a multidisciplinary approach, combining elements of plasma physics, magnetohydrodynamics, astrophysics, and even quantum mechanics. Each new discovery about the Parker spiral brings us closer to understanding the Sun's role in shaping the universe around us, from the smallest particles of the solar wind to the vast interstellar medium. But the journey of discovery doesn't stop there. Every answer we uncover about the Parker spiral raises new questions, driving us to look deeper and think more broadly about the interconnected systems that govern the cosmos. What other secrets might the Parker spiral hold? Could it help us unlock new technologies, protect our planet, or even find life beyond Earth? The possibilities are as infinite as the universe itself. The Parker spiral's role in the broader context of space science cannot be overstated. It's not just a fascinating manifestation of the Sun's influence, but a vital clue in understanding the relationship between stars, planets, and interstellar space. As researchers dig deeper into its mysteries, they reveal how interconnected and fragile these systems truly are. One particularly compelling area of research revolves around the Parker spiral's interaction with cosmic rays. Cosmic rays are high-energy particles originating from outside the solar system, often from supernova explosions or other extreme cosmic events. As these particles enter the heliosphere, the Sun's protective bubble formed by the solar wind, they encounter the Parker spiral's magnetic fields. These fields act as a kind of filter, deflecting many cosmic rays and shielding the inner solar system from their harmful effects. However, the effectiveness of this shield isn't constant. During periods of low solar activity, when the solar wind is weaker, more cosmic rays can penetrate the heliosphere. Conversely, during periods of high solar activity, the stronger solar wind and more chaotic Parker spiral provide better protection. This interplay has significant implications for space weather and human exploration. Increased cosmic ray exposure during solar minimums poses a heightened risk for astronauts on long-duration missions, such as those to Mars or beyond. Understanding the dynamics of the Parker spiral is, therefore, critical for developing strategies to protect future spacefarers. The Parker spiral also plays a significant role in shaping the heliospheric current sheet, a vast, wavy structure that separates regions of the solar wind with opposite magnetic polarity. This sheet, which extends throughout the heliosphere, is sometimes referred to as the ballerina skirt, because of its undulating shape. The Parker spiral's rotation drives the formation of this current sheet, adding another layer of complexity to the solar wind's behavior. As the heliospheric current sheet moves outward with the solar wind, it interacts with planets, comets, and other objects in the solar system. These interactions can have profound effects. For instance, when Earth passes through the current sheet, we often experience geomagnetic storms and other space weather phenomena. Understanding these interactions is essential for predicting their impact on satellites, power grids, and other critical infrastructure. The Parker Solar Probe, launched in 2018, has been instrumental in advancing our understanding of the Parker spiral and its associated phenomena. As the spacecraft ventures closer to the Sun than any previous mission, it collects unprecedented data on the solar wind, magnetic fields, and the Sun's corona. One of its key objectives is to unravel the mechanisms that accelerate the solar wind and create the Parker spiral's structure. Initial findings from the Parker Solar Probe have already challenged some long-held assumptions. For example, the mission has revealed that the solar wind is far more dynamic and turbulent than previously thought. Magnetic switchbacks, or sudden reversals in the solar wind's magnetic field, appear to be more common than expected. These switchbacks could play a crucial role in shaping the Parker spiral, but their origin remains a mystery. Some researchers speculate that they might be linked to magnetic reconnection events in the Sun's corona, while others suggest they could arise from the turbulence generated as the solar wind streams outward. The data collected by the Parker Solar Probe also provides new insights into the processes that heat the Sun's corona to millions of degrees, far hotter than the Sun's surface. This coronal heating problem has puzzled scientists for decades and is closely tied to the behavior of the Parker spiral. The energy required to heat the corona and accelerate the solar wind must come from the Sun's magnetic fields, but the exact mechanisms are still unclear. By studying the Parker spiral, researchers hope to uncover these mechanisms and solve one of the Sun's greatest mysteries. As our understanding of the Parker spiral deepens, it also raises intriguing questions about other stars. Do all stars with magnetic fields and stellar winds produce similar spirals? If so, how do these spirals differ based on a star's size, age, and activity level? Studying the Parker spiral provides a framework for exploring these questions and understanding how magnetic fields shape the environments around stars throughout the galaxy. Moreover, the Parker spiral serves as a reminder of the Sun's profound influence on our lives. From the auroras that light up polar skies to the disruptions caused by geomagnetic storms, the effects of the Sun's magnetic fields and solar wind are tangible and immediate. Yet, they are also deeply complex, woven into the fabric of space itself. The Parker spiral is a testament to this complexity, a dynamic and ever-changing structure that reflects the Sun's power and the interconnectedness of the solar system. Even as we continue to make strides in understanding the Parker spiral, there's a sense that we are only scratching the surface. Each new discovery opens the door to further questions, pushing the boundaries of what we know and challenging us to think in new ways. The Parker spiral is more than just a scientific curiosity. It's a gateway to understanding the fundamental forces that shape our universe. As we look to the future, the study of the Parker spiral will undoubtedly remain a focal point for solar and space physics. With missions like the Parker Solar Probe and the European Space Agency's Solar Orbiter, we are poised to unlock more of its secrets and gain a deeper understanding of the Sun's magnetic influence. These insights will not only enhance our knowledge of the Sun and its effects on the solar system but also help us prepare for the challenges and opportunities of a future where humanity ventures further into space. The Parker spiral, with its elegant yet complex structure, reminds us of the beauty and mystery of the cosmos. It is a dance of magnetic fields and solar winds, a testament to the dynamic forces that shape our universe. And as we continue to study it, we are reminded of the endless possibilities that await us in the exploration of space. The Parker spiral represents not just the Sun's immediate influence but also a key to understanding the broader mechanics of stellar systems. It is a microcosm of the dynamic processes at play in stars across the galaxy, offering clues about how magnetic fields and winds influence their surrounding environments. The Sun, through its magnetic reach, offers us a window into these universal principles, and the Parker spiral serves as the map that traces this connection. The heliosphere, the vast bubble of space dominated by the Sun's magnetic field and solar wind, is shaped in no small part by the Parker spiral. This region acts as a shield, warding off much of the galactic radiation that might otherwise bombard the planets within. It defines the boundary between the solar system and interstellar space, known as the heliopause. The interaction between the outward-flowing solar wind and the incoming interstellar medium creates a fascinating boundary zone where the Parker spiral plays a crucial role. One fascinating aspect of the Parker spiral's influence is how it governs the movement and behavior of charged particles within the heliosphere. The spiraling magnetic field lines create pathways that particles can follow, guiding their trajectories throughout the solar system. This has practical implications for space travel and exploration, as spacecraft must navigate these magnetic highways to optimize their journeys and minimize exposure to radiation. For instance, missions to Mars and beyond must consider the Parker spiral's orientation and dynamics when planning their trajectories. By understanding how solar wind particles flow along the spiral, engineers can design spacecraft that are better equipped to withstand the challenges posed by space weather. This is particularly critical during periods of high solar activity, when the spiral becomes more chaotic, and the risk of solar storms increases. The Parker spiral also has a significant impact on the distribution of dust in the solar system. As the solar wind flows outward, it interacts with interplanetary dust, creating a region known as the dust-free zone near the Sun. This zone is shaped by the spiral's magnetic fields, which can trap or expel charged dust particles depending on their properties. This interplay affects the composition of the solar wind and provides insights into the processes that govern the early stages of planet formation in other stellar systems. Beyond its physical effects, the Parker spiral offers a profound lesson in how small-scale processes can have far-reaching consequences. The spiral's shape and behavior are dictated by the rotation of the Sun, a relatively simple motion on a cosmic scale. Yet, this simple motion gives rise to a structure that extends across billions of kilometers, influencing everything within the heliosphere and beyond. It is a reminder of the interconnectedness of the cosmos, where even the smallest forces can have a profound impact on the grandest scales. As researchers continue to study the Parker Spiral, they are also exploring its potential as a tool for understanding space weather. By mapping the spiral and tracking its changes over time, scientists can develop better models for predicting solar storms and their effects on Earth. This is particularly important as our reliance on satellite technology grows. From GPS systems to communication networks, many aspects of modern life depend on the stability of space-based infrastructure. Understanding the Parker Spiral can help us protect these systems from the disruptions caused by solar activity. The study of the Parker Spiral also raises intriguing questions about the Sun's long-term behavior. As the Sun ages, its magnetic field will gradually weaken, altering the shape and intensity of the Parker Spiral. This evolution will have far-reaching effects on the heliosphere and the solar system as a whole. By studying the current behavior of the spiral, scientists can gain insights into the future of our solar system and the conditions that might prevail as the Sun transitions into its next phase of life. The Parker Spiral is not just a scientific curiosity. It is a bridge to understanding the profound connections that link the Sun, the planets, and the broader galaxy. It embodies the dynamic and ever-changing nature of the cosmos, reminding us that even the most familiar objects, like the Sun, are full of mysteries waiting to be uncovered. As we continue to study this fascinating structure, we move closer to unlocking the secrets of the universe and our place within it. Perhaps what is most remarkable about the Parker Spiral is how it encapsulates the essence of scientific discovery. It is a phenomenon that is both beautiful and functional, elegant in its simplicity yet endlessly complex in its implications. It challenges us to think beyond the confines of our own planet and consider the forces that shape the vast expanse of space. The journey to understand the Parker Spiral is far from over. With each new mission and observation, we peel back another layer of this cosmic enigma, revealing new insights and posing new questions. The spiral is a testament to the enduring power of curiosity and the human drive to explore the unknown. It reminds us that even in the seemingly infinite vastness of space, there is a sense of order and structure, a reminder that the universe, in all its complexity, is governed by the same fundamental principles. As we look to the future, the Parker Spiral will continue to be a source of inspiration and discovery. Its study will drive advances in technology, deepen our understanding of the Sun and its influence, and expand our knowledge of the universe. It is a symbol of the interconnectedness of all things, a reminder that we are part of a vast and dynamic cosmos, and a testament to the power of science to illuminate the mysteries of the world around us. The Parker Spiral's significance is deeply rooted in its ability to act as both a tangible and theoretical framework for exploring how stars influence their surroundings. This spiraling magnetic structure is far more than a fascinating visualization of the Sun's magnetic field in motion. It is a dynamic phenomenon that profoundly affects the behavior of charged particles, the solar wind, and even the delicate balance of the heliosphere. Each revelation about the Parker Spiral opens up new avenues for understanding not only the Sun but also other stellar systems across the galaxy. One of the most exciting aspects of the Parker Spiral is how its study informs our understanding of magnetic fields beyond the Sun. Every star generates magnetic fields that interact with their stellar winds, and these fields likely form structures similar to the Parker Spiral. The shape, strength, and dynamics of these spirals could vary depending on a star's rotation rate, magnetic activity, and composition. The Parker Spiral thus provides a template for studying other stars and their influence on their planetary systems. For instance, consider stars that are much more massive or active than the Sun. These stars likely have magnetic fields far more intense, and solar winds much faster than those of our Sun. The resulting spirals could be denser, more chaotic, or extend much further into space. By comparing these hypothetical spirals to the Parker Spiral, scientists can extrapolate how these differences might impact planetary environments and even the habitability of distant worlds. Furthermore, the Parker Spiral study sheds light on the phenomenon of stellar evolution. As stars age, their rotation slows, and their magnetic fields weaken. This gradual change alters the structure of the Parker spiral and the heliosphere, reducing their ability to shield planets from cosmic rays. For Earth, this protective shield is essential to maintaining a stable environment for life. The weakening of the Sun's magnetic field and the evolution of the Parker spiral will undoubtedly influence the long-term habitability of our planet, providing a preview of the challenges humanity may face billions of years from now. Another crucial area of research involves the interaction between the Parker spiral and interstellar space. The outermost boundary of the heliosphere, where the solar wind meets the interstellar medium, is shaped by the outward extension of the spiral. This interaction creates a turbulent region where the solar wind slows, compresses, and mixes with interstellar particles. By studying how the Parker spiral interacts with these external forces, scientists gain a better understanding of the Sun's role in protecting the solar system from galactic radiation and how similar processes might occur around other stars. This boundary, known as the heliopause, has been a subject of intense study, particularly with the data provided by the Voyager 1 and Voyager 2 spacecraft. These probes, now traveling beyond the heliopause, have provided invaluable insights into how the Parker spiral and the solar wind gradually give way to the influence of interstellar forces. The Parker spiral's imprint remains evident even at these distant reaches, highlighting the Sun's far-reaching influence and the interconnectedness of the solar system. The Parker spiral's impact extends even to the smallest particles in the solar system. Dust grains, for instance, experience the influence of the spiral's magnetic field as they move through the solar wind. Charged dust particles can become entrained in the spiral's magnetic field lines, altering their trajectories and potentially influencing their role in planetary formation. By studying these interactions, scientists hope to better understand how magnetic fields influence the early stages of planetary and moon development, both in our solar system and in others. The Parker Solar Probe continues to play a pivotal role in unraveling these mysteries. As the spacecraft ventures closer to the Sun than ever before, it is collecting data on the magnetic fields and plasma flows that drive the Parker spiral's formation. Each pass by the Sun provides new insights into the dynamics of the solar corona, the birthplace of the solar wind. These observations are critical for solving long-standing mysteries about the Sun's behavior and its impact on the solar system. One intriguing discovery from the Parker Solar Probe is the nature of magnetic switchbacks, sharp, sudden reversals in the direction of the solar wind's magnetic field. These switchbacks appear to be more frequent near the Sun, suggesting that they may play a role in the acceleration of the solar wind and the formation of the Parker spiral. Understanding these phenomena could revolutionize our understanding of how the Sun's energy is transferred into the solar wind and how this process shapes the spiral. Moreover, the Parker spiral's influence is not limited to the solar system's inner regions. It extends outward, interacting with planets, moons, and even distant Kuiper belt objects. As the spiral's magnetic field lines pass by these celestial bodies, they can induce electric currents in their atmospheres or surfaces, creating auroras and other phenomena. By studying these interactions, scientists can gain new insights into the magnetic environments of other worlds and the role of the Sun in shaping their properties. The Parker spiral is also a critical factor in understanding space weather. Solar storms, driven by eruptions on the Sun's surface, propagate through the Parker spiral, influencing its structure and dynamics. These disturbances can disrupt satellite communications, damage power grids, and pose risks to astronauts. By studying the Parker spiral's behavior during these events, scientists aim to develop better predictive models and mitigation strategies, safeguarding our technology-dependent society. As humanity looks to the stars, the Parker spiral serves as a reminder of the Sun's profound influence on the solar system. It is a testament to the dynamic forces that shape our environment, a symbol of the interconnectedness of the cosmos, and a gateway to understanding the mysteries of other stellar systems. The Parker spiral is more than a scientific curiosity. It is a bridge between the familiar and the unknown, a guide to the forces that govern the universe. Every new discovery about the Parker spiral deepens our appreciation for the complexity and beauty of the cosmos. It is a structure that embodies both the simplicity of the Sun's rotation and the profound complexity of its interactions with the solar system. As we continue to study this fascinating phenomenon, we are reminded of the endless possibilities that await us in the exploration of space. The Parker Spiral continues to astonish scientists with its dynamic interplay between simplicity and complexity, acting as a celestial blueprint that connects the Sun's magnetic field to the farthest reaches of the solar system. Its existence and behavior have profound implications for a range of scientific fields, from astrophysics to planetary science, and even to space exploration. It is through the lens of this remarkable spiral that we begin to decode some of the most elusive mysteries of the universe. One critical aspect of the Parker Spiral is its ability to shape the distribution of charged particles, which has far-reaching consequences for the interplanetary medium. The solar wind, made up of electrons and protons, flows outward from the Sun, guided by the magnetic field lines of the Parker Spiral. These particles carry energy and magnetic information, making them an essential component in understanding how energy is transferred throughout the solar system. A particularly fascinating phenomenon occurs when these particles encounter magnetic reconnection sites, regions where magnetic field lines break and rejoin. This process releases massive amounts of energy, further accelerating particles and influencing the structure of the Parker Spiral. Magnetic reconnection is not limited to the Sun, it is observed throughout the cosmos, from planetary magnetospheres to distant galaxies. Studying how it manifests within the Parker Spiral provides a localized laboratory for unraveling its universal significance. The Parker Spiral's interaction with the solar system's planets, especially those with magnetic fields of their own, creates an intricate ballet of forces. Planets like Earth, with its strong magnetosphere, carve out protective bubbles within the Parker Spiral, deflecting much of the solar wind. However, during intense solar storms, the Parker Spiral's magnetic fields can compress Earth's magnetosphere, causing geomagnetic storms. These events can produce breathtaking auroras but also wreak havoc on power grids and communication networks. For planets without magnetic fields, such as Mars and Venus, the story is different. The Parker Spiral's magnetic field lines can directly interact with their upper atmospheres, stripping away particles and contributing to atmospheric loss over time. This raises compelling questions about the role of the Parker Spiral in the evolution of planetary environments. Did it play a role in Mars losing most of its atmosphere, transforming it from a potentially habitable world into the arid desert it is today? Could similar processes be occurring on exoplanets orbiting other stars? Beyond its immediate effects on planets, the Parker Spiral also shapes the behavior of cosmic rays, high-energy particles originating from outside the solar system. As cosmic rays travel toward the Sun, they encounter the Parker Spiral, which acts as a barrier. The spiral's magnetic fields scatter and decelerate these particles, reducing the number that reach the inner solar system. This protective effect, known as the heliospheric modulation of cosmic rays, has important implications for both the evolution of life on Earth and the safety of future space missions. Understanding the Parker Spiral's role in modulating cosmic rays also informs us about the heliosphere's structure and its interactions with the interstellar medium. The heliosphere is not a static bubble, it is constantly reshaped by the solar wind and the Parker Spiral, which extend outward to define its boundaries. The spiral's influence can even be detected in the termination shock, where the solar wind slows abruptly, and in the heliopause, where the solar wind meets the interstellar medium. These distant regions are critical for understanding the Sun's influence beyond the planets and into interstellar space. The Voyager spacecraft have provided groundbreaking data on these regions, revealing the Parker Spiral's enduring imprint even at the edge of the solar system. As these spacecraft journey into interstellar space, they continue to measure how the spiral transitions into the chaotic environment beyond the heliosphere. These observations offer a glimpse into how the Sun's magnetic influence compares to that of other stars, contributing to a broader understanding of stellar magnetospheres and their interactions with the galaxy. The study of the Parker Spiral is not limited to observations. It also involves complex simulations and models. Scientists use supercomputers to recreate the Sun's magnetic field and solar wind in 3 dimensions, allowing them to visualize and predict the spiral's behavior under various conditions. These models incorporate data from spacecraft like the Parker Solar Probe, which provides unprecedented close-up measurements of the Sun's magnetic fields, plasma, and energetic particles. Together, these tools enable scientists to refine their understanding of the Parker spiral and its many roles within the solar system. One of the most exciting applications of this research is its potential to improve space weather forecasting. By understanding how the Parker spiral propagates disturbances from the Sun, scientists can better predict when and where solar storms will strike. This information is crucial for protecting satellites, power grids, and astronauts, especially as humanity becomes more dependent on space-based technology and plans missions to the Moon, Mars, and beyond. As we expand our presence in space, the Parker spiral will play an increasingly important role in shaping the environments we encounter. Spacecraft traveling beyond Earth's orbit must navigate the spiral's magnetic fields and the charged particles they guide. Understanding these interactions will be essential for ensuring the safety and success of future missions. For example, spacecraft shielding designs could be optimized based on the Parker spiral's influence, reducing the risks posed by radiation and particle impacts. The Parker spiral also holds the key to unlocking broader questions about the universe's magnetic fields. Magnetic fields are ubiquitous in the cosmos, influencing everything from the formation of stars and galaxies to the behavior of black holes and neutron stars. By studying the Parker spiral, we gain a microcosmic view of these larger processes, bridging the gap between our solar system and the broader universe. At its core, the Parker spiral is a testament to the Sun's dynamic nature and its far-reaching influence. It is a reminder that the Sun is not a static ball of gas but a living, breathing star whose magnetic heart beats through the solar system. Each twist of the spiral tells a story of motion, interaction, and transformation, connecting the Sun to its planets, its distant boundaries, and even the stars beyond. The Parker spiral is more than a scientific curiosity. It is a symbol of the interconnectedness of the cosmos. It shows us that even the simplest motions, like the Sun's rotation, can give rise to complex and beautiful structures that shape our universe. It invites us to look closer, to ask questions, and to seek answers, not just about the Sun, but about the forces that govern the stars and the galaxies they inhabit. The Parker spiral remains one of the most compelling features of the solar system's magnetic and energetic landscape. Its influence is deeply intertwined with the origins of the solar wind, the dynamics of the heliosphere, and even the behavior of distant cosmic rays. Yet what truly sets the Parker spiral apart is its ability to provide a framework for understanding not just our Sun, but the magnetic interactions of stars across the universe. The interplay between the Parker spiral and the solar wind is especially fascinating. The solar wind itself is a phenomenon that eluded scientists for decades before Eugene Parker's groundbreaking work in the 1950s. It is now understood to be a constant stream of charged particles, mainly electrons, protons, and alpha particles, that flow outward from the Sun. This outward movement is driven by the intense heat of the solar corona, which reaches temperatures of millions of degrees Celsius, allowing particles to escape the Sun's gravitational pull. As these particles stream outward, they carry with them magnetic field lines rooted in the Sun's surface. Because the Sun rotates, these magnetic field lines are twisted into the Parker spiral. This simple yet profound relationship between the Sun's rotation and the outward flow of the solar wind is the key to understanding the spiral's shape and behavior. The speed of the solar wind plays a crucial role here. It determines how tightly or loosely the spiral is wound. Faster solar wind streams produce more stretched-out spirals, while slower streams create more tightly wound ones. The Sun's activity cycle further complicates this relationship. Over its approximately 11-year cycle, the Sun's magnetic field undergoes dramatic changes, flipping its polarity and intensifying or weakening in strength. These changes are mirrored in the Parker spiral, which becomes more chaotic and irregular during periods of high solar activity, known as solar maximum. During these times, the Sun emits more intense bursts of solar wind, often accompanied by powerful eruptions such as solar flares and coronal mass ejections, CMEs. Coronal mass ejections are particularly significant in the context of the Parker spiral. These massive expulsions of plasma and magnetic fields can distort the spiral as they travel outward, creating shock waves that propagate through the solar system. When a CME interacts with Earth, it can compress the planet's magnetosphere and trigger geomagnetic storms. These events not only produce dazzling auroras but also pose serious risks to satellites, power grids, and even human health in space. The Parker Spiral also acts as a conduit for energy and magnetic information, connecting the Sun to distant regions of the heliosphere. This connection is vividly illustrated in the phenomenon of interplanetary coronal mass ejections, ICMEs. Unlike ordinary solar wind streams, ICMEs carry their own magnetic fields, which can interact with the Parker Spiral in complex ways. These interactions can create regions of enhanced or depleted magnetic field strength, influencing the movement of charged particles and the dynamics of the solar wind. As the Parker Spiral extends outward, it defines the structure of the heliosphere, the vast bubble of space dominated by the solar wind and the Sun's magnetic field. The heliosphere acts as a shield, protecting the solar system from high-energy cosmic rays that originate outside the galaxy. However, the Parker Spiral's role within the heliosphere is not merely defensive. It actively shapes the environment within this bubble. By modulating the flow of cosmic rays and guiding the solar wind, the spiral helps maintain the delicate balance of forces that defines the heliosphere. The boundaries of the heliosphere offer a unique perspective on the Parker Spiral's influence. At the termination shock, where the solar wind slows to subsonic speeds, the spiral structure begins to break down, giving way to a more chaotic and turbulent environment. Beyond this lies the heliopause, the outermost boundary of the heliosphere, where the solar wind meets the interstellar medium. Even here, the remnants of the Parker Spiral can be detected, revealing its enduring impact on the solar system's outermost reaches. The Parker Spiral also offers insights into the processes that shape other stellar systems. Stars similar to the Sun are likely to generate their own versions of the Parker Spiral, governed by their rotation rates, magnetic fields, and stellar winds. By studying the Parker Spiral in detail, scientists can develop models that apply to these distant stars, helping to explain phenomena such as stellar flares, exoplanetary space weather, and the formation of stellar magnetospheres. For example, rapidly rotating stars may produce tightly wound spirals with stronger magnetic fields, while slower rotators might create more stretched-out configurations. These variations could influence the habitability of exoplanets orbiting such stars. A tightly wound spiral with intense magnetic activity might expose planets to frequent radiation storms, stripping away their atmospheres and making them inhospitable for life. Conversely, a more stable spiral might create a protective environment, shielding planets from cosmic rays and enabling the development of life. The implications of the Parker Spiral extend even to the interstellar medium. As the spiral interacts with this vast, diffuse environment, it contributes to the complex network of magnetic fields and plasma that pervades the galaxy. Understanding how the Parker Spiral fits into this larger picture is a key goal of modern astrophysics. By studying the spiral's influence on interstellar particles and fields, scientists can gain insights into the processes that govern the evolution of galaxies and the dynamics of the cosmic web. In many ways, the Parker Spiral serves as a bridge between the microcosm of the solar system and the macrocosm of the universe. Its elegant, helical structure embodies the principles of motion, energy, and magnetism that are fundamental to the cosmos. It reminds us that even the most familiar celestial objects, like the Sun, can harbor profound mysteries waiting to be unraveled. The Parker Spiral also holds promise for future exploration. Missions like the Parker Solar Probe, which is currently studying the Sun at unprecedented close range, are providing invaluable data on the spiral's structure and behavior. These observations are helping scientists refine their models and develop new theories about the Sun's magnetic field and its interactions with the solar wind. As humanity prepares to venture deeper into space, the Parker Spiral will remain a vital focus of research. Whether we are sending spacecraft to the outer planets, building colonies on Mars, or exploring the interstellar medium, our understanding of the Parker Spiral will shape how we navigate and adapt to these new environments. It is a reminder that even in the vastness of space, the Sun's influence is never far away, guiding and shaping the paths we take. The Parker Spiral's enduring influence reaches far beyond its immediate domain, extending into the dynamics of cosmic rays and their interaction with the solar system. Cosmic rays, which are high-energy particles originating from outside the heliosphere, must navigate the Parker spiral's complex magnetic structure as they journey toward Earth. This interaction creates a fascinating interplay between the forces of the Sun and the particles of the galaxy, shaping both the radiation environment of our solar system and the scientific questions that drive astrophysical research. One of the key processes influenced by the Parker spiral is the modulation of cosmic rays. As these particles approach the solar system, they encounter the outward-flowing solar wind and the embedded magnetic fields of the spiral. These fields act as barriers, deflecting, slowing, and scattering cosmic rays, altering their paths and energies. This phenomenon, known as solar modulation, varies with the Sun's activity cycle. During periods of high solar activity, the Sun's magnetic field is stronger, and the Parker spiral becomes more effective at shielding the inner solar system from cosmic rays. Conversely, during solar minimum, the spiral's magnetic influence weakens, allowing more cosmic rays to penetrate. The effects of cosmic ray modulation are far-reaching. For example, variations in cosmic ray intensity can influence Earth's atmosphere, potentially affecting cloud formation, weather patterns, and even long-term climate trends. While the exact mechanisms remain a subject of scientific debate, the Parker spiral's role as a cosmic ray filter underscores its importance in the broader context of planetary and environmental science. Additionally, cosmic ray interactions with the Parker spiral provide a unique opportunity to study fundamental processes in plasma physics and magnetohydrodynamics. By analyzing how cosmic rays are deflected, scientists can gain insights into the structure and behavior of the spiral's magnetic fields. This research has implications not only for understanding the Sun but also for developing models of other astrophysical systems, such as pulsar wind nebulae, magnetars, and active galactic nuclei, where similar processes may occur on vastly larger scales. The Parker spiral also has a profound impact on space weather forecasting. Space weather refers to the conditions in space that can affect Earth's technological systems and human activities. These conditions are shaped by the interplay of the solar wind, the Parker spiral, and the Earth's magnetosphere. For instance, when a coronal mass ejection interacts with the Parker spiral, it can create shock waves that propagate through the solar wind. These shock waves can intensify geomagnetic storms, leading to disruptions in satellite communications, GPS systems, and power grids on Earth. Understanding the Parker spiral is thus critical for predicting and mitigating the effects of space weather. By studying the spiral's structure and its interactions with solar eruptions, scientists can develop more accurate models and forecasts. This research is especially important as humanity becomes increasingly reliant on space-based technologies and as plans for crewed missions to the Moon, Mars, and beyond take shape. The Parker spiral is not just a scientific curiosity, it is a practical concern for the safety and success of future space exploration. The Parker Solar Probe, launched in 2018, represents a major milestone in our quest to understand the Parker spiral and its implications. By traveling closer to the Sun than any previous spacecraft, the probe is able to observe the solar wind and the spiral's magnetic fields at their source. Its findings have already begun to challenge existing theories, revealing new details about the acceleration of the solar wind, the formation of magnetic switchbacks, and the behavior of the Sun's corona. One of the most intriguing discoveries of the Parker Solar Probe is the presence of magnetic switchbacks, sudden reversals in the direction of the magnetic field lines embedded in the solar wind. These switchbacks appear to be a fundamental feature of the Parker spiral, providing clues about the processes that generate and shape the solar wind. Some researchers suggest that switchbacks may be caused by jets of plasma erupting from the Sun's surface, while others propose that they result from interactions between the solar wind and the Sun's magnetic field. Whatever their origin, switchbacks represent a new frontier in our understanding of the Parker spiral and its dynamic behavior. The Parker spiral's influence is not limited to our solar system. Its structure and behavior provide a template for studying magnetic fields and plasma flows in other stellar systems. For example, stars with strong magnetic fields and fast rotation rates are likely to produce tightly wound spirals, while stars with weaker fields or slower rotation rates may generate more diffuse configurations. These variations have important implications for the habitability of exoplanets, as they influence the intensity and variability of space weather around those stars. In particular, the Parker spiral offers insights into the environments of M-dwarf stars, which are the most common type of star in the galaxy. M-dwarfs are known for their intense magnetic activity and frequent flares, which can produce extreme versions of the Parker spiral. Understanding how these spirals interact with exoplanets could help scientists assess the potential for life in these systems and identify candidates for further exploration. The study of the Parker spiral also intersects with research on the interstellar medium, the vast expanse of gas, dust, and magnetic fields that fills the galaxy. As the solar wind and the Parker spiral extend outward, they interact with the interstellar medium at the boundaries of the heliosphere. This interaction creates a complex and dynamic region where the forces of the Sun and the galaxy collide. By studying this region, scientists can gain insights into the processes that shape not only our solar system but also the broader structure of the Milky Way. The Voyager spacecraft, which have traveled beyond the heliopause into interstellar space, provide valuable data on the Parker spiral's influence at the solar system's outermost edges. These observations reveal how the spiral's magnetic fields interact with interstellar particles and fields, creating waves, turbulence, and other phenomena that illuminate the physics of the interstellar medium. Voyager's findings complement those of the Parker Solar Probe, providing a comprehensive picture of the spiral's behavior across vast distances. The Parker spiral's legacy extends even further, shaping our understanding of cosmic magnetism on all scales. From the twisting fields of young stars to the magnetic spirals of galaxies, the principles embodied in the Parker spiral resonate throughout the universe. By studying this elegant structure, we uncover the fundamental laws that govern the cosmos and deepen our appreciation for the interconnectedness of all things. As we continue to explore the mysteries of the Parker spiral, we are reminded of the profound beauty and complexity of the natural world. It is a testament to the power of human curiosity and ingenuity that we can unravel the secrets of something as vast and dynamic as the Sun's magnetic field. In doing so, we not only advance our scientific knowledge but also forge a deeper connection to the universe that surrounds us. The Parker spiral serves as a profound reminder of how seemingly simple physical principles can create intricate and far-reaching phenomena. As the Sun rotates, its magnetic field drags through the solar wind, forming the vast and spiraling structure that extends across the heliosphere. What's remarkable is how this mechanism, rooted in fundamental plasma physics and electromagnetism, governs not only the behavior of the solar wind but also impacts the entire solar system and beyond. One of the enduring mysteries surrounding the Parker spiral is how it contributes to the larger dynamics of the heliosphere itself. The heliosphere is the vast bubble of charged particles and magnetic fields generated by the Sun that envelopes the solar system, shielding it from the harsher cosmic environment of interstellar space. The Parker spiral forms the backbone of this structure, influencing how the solar wind flows outward and interacts with the heliosphere's outer boundaries, particularly the heliopause, the region where the solar wind meets the interstellar medium. The heliosphere, shaped by the Parker spiral, acts as a protective shield, blocking much of the galactic cosmic radiation that would otherwise bombard the planets within. This shielding effect has profound implications for life on Earth and the potential habitability of other worlds within the solar system. By studying the Parker spiral, scientists gain critical insights into how the Sun's magnetic influence creates this cocoon and how its dynamics might evolve over time. Another intriguing aspect of the Parker spiral is its role in mediating solar-terrestrial relationships. The interaction between the Sun's magnetic field and the Earth's magnetosphere is a complex and dynamic process, heavily influenced by the spiral's configuration. When solar wind particles, guided by the Parker spiral, collide with Earth's magnetic field, they can create geomagnetic storms and auroras. These events, while visually stunning, can have significant consequences for modern technology. For instance, geomagnetic storms can disrupt satellite operations, cause fluctuations in GPS signals, and even induce currents in power grids that can lead to blackouts. Understanding the Parker spiral's structure and how it channels solar wind toward Earth is therefore not just a matter of scientific curiosity, but a practical necessity for protecting our technological infrastructure. Space weather forecasting relies heavily on models of the Parker spiral to predict when and where these solar disturbances will strike, allowing for timely precautions to mitigate their effects. One of the most fascinating discoveries linked to the Parker spiral is the phenomenon of magnetic reconnection within its framework. Magnetic reconnection occurs when oppositely directed magnetic field lines break and reconnect, releasing vast amounts of energy in the process. This phenomenon plays a key role in driving explosive solar events such as solar flares and coronal mass ejections. These events, in turn, feed into the Parker spiral, altering its structure and amplifying its influence on the solar wind. Magnetic reconnection within the Parker spiral also offers a window into universal processes occurring in plasmas throughout the cosmos. By studying this phenomenon in the context of the Sun, researchers can draw parallels to similar processes in other astrophysical environments, such as the magnetospheres of distant planets, the disks of accreting black holes, or the jets of active galactic nuclei. This cross-disciplinary approach highlights the Parker spiral's significance as a model system for understanding magnetic phenomena on multiple scales. The Sun's magnetic field, and by extension the Parker spiral, is not a static entity. It undergoes periodic reversals as part of the solar activity cycle, which lasts approximately 11 years. During this cycle, the Sun's magnetic poles flip, and its magnetic field becomes increasingly chaotic before settling into a new configuration. These reversals have a profound impact on the Parker spiral, altering its structure and the behavior of the solar wind. During periods of high solar activity, known as solar maximum, the Parker spiral becomes more turbulent, with increased levels of magnetic complexity and variability. This turbulence has cascading effects on the solar wind and its interactions with planets and the heliosphere. By contrast, during solar minimum, the spiral becomes more stable and predictable. Studying these cyclical changes provides valuable insights into the Sun's magnetic dynamo and the forces that drive its variability. The implications of the Parker spiral also extend to the realm of space exploration. As humanity ventures beyond Earth's orbit, understanding the Parker spiral becomes increasingly critical for the safety of astronauts and spacecraft. The solar wind, guided by the spiral, carries with it a barrage of charged particles that can pose significant radiation risks to unprotected humans and electronics. Missions to the Moon, Mars, and beyond must account for the Parker spiral's influence on space weather to ensure their success. For example, understanding how the Parker spiral shapes the distribution of solar energetic particles can help mission planners design more effective shielding and develop strategies for avoiding high radiation zones. The spiral also informs the placement and operation of deep space probes, which rely on its dynamics to navigate and communicate effectively. In this way, the Parker spiral is not just an abstract concept but a practical concern for the future of space exploration. The study of the Parker spiral is also shedding light on the Sun's interactions with the broader galaxy. As the solar wind flows outward and encounters the interstellar medium, it creates a complex interface that is influenced by the spiral's structure. This interface, known as the heliosheath, is a turbulent region where solar and interstellar forces collide. By examining how the Parker spiral shapes this boundary, scientists can gain insights into the Sun's place within the galactic environment and the processes that govern star-planet interactions across the universe. In many ways, the Parker spiral is a microcosm of larger cosmic dynamics. Its spiral shape mirrors the structure of spiral galaxies, while its magnetic fields reflect the universal principles that govern plasmas throughout the cosmos. By unraveling the mysteries of the Parker spiral, we not only deepen our understanding of the Sun but also uncover connections that span the universe, linking the smallest scales of particle motion to the grandest structures in the cosmos. The Parker spiral represents a remarkable interplay of forces: rotation, magnetism, and plasma flow, all orchestrated by the Sun. It is a dynamic and ever-changing structure that influences everything from the behavior of cosmic rays to the conditions of space weather to the habitability of planets. Through missions like the Parker Solar Probe and ongoing research into solar physics, we are steadily unraveling its secrets, revealing a story of cosmic complexity and interconnectedness that continues to inspire and amaze. The deeper we delve into the study of the Parker spiral, the more it becomes clear that this phenomenon is not just a localized aspect of the Sun's behavior but a key feature with far-reaching consequences. As we continue to explore the intricate web of solar dynamics, it becomes increasingly evident how interconnected the various forces at play are. The Parker spiral, though a relatively recent discovery in terms of our understanding, holds the key to unlocking many mysteries about the solar wind, the Sun's magnetic field, and even broader cosmic phenomena. To fully grasp the significance of the Parker spiral, it's important to consider how it impacts the movement and flow of the solar wind. This continuous stream of charged particles emanates from the Sun, carrying with it not only the Sun's magnetic influence but also particles that play a key role in shaping the environments of other planets, moons, and space bodies. The Sun's rotation combined with its magnetic field is what makes this solar wind a spiral. The wind travels outward, yet the rotation of the Sun twists it into this shape as it moves. This twisting effect is critical because it affects everything in the heliosphere. The heliosphere itself is an expansive bubble that extends far beyond the planets of the solar system. This region is filled with the solar wind, but due to the Parker spiral, the wind flows in a spiraling motion that can change how particles interact with various objects. It means that particles traveling through space won't simply move in a straight line. They will follow the shape and direction determined by the Sun's magnetic rotation. As the solar wind continues to move outward, it continually influences the space environment, interacting with other cosmic forces and particles. The Sun's magnetic field is what causes the solar wind to spiral outward. As the Sun rotates on its axis, it drags its magnetic field lines along with it. Since the Sun is not a solid object but a ball of plasma, different parts of it rotate at different speeds, which leads to the twisting of magnetic field lines. This twisting action plays a key role in shaping the spiral that we see in the solar wind. It's not just a random pattern, it's the result of the Sun's dynamic nature and the way in which its internal and external forces interact. We can trace the importance of the Parker spiral not only to the solar wind but also to the magnetic field interactions between the Sun and the planets. For example, Earth's magnetosphere is continually shaped and altered by the solar wind that travels along the path of the Parker spiral. When the solar wind reaches Earth, its influence is felt as geomagnetic storms. These storms occur when the charged particles from the Sun interact with Earth's magnetic field, causing disturbances in our planet's electrical systems, satellite operations, and communication networks. Understanding the Parker spiral and its relationship with solar activity is vital for predicting space weather events. These events can range from minor solar flares to massive coronal mass ejections, CMEs, both of which can have profound effects on technological systems here on Earth. The more accurately we can model the Parker spiral, the better we can forecast when such events are likely to occur and how intense they may be. With space exploration becoming a more integral part of humanity's future, understanding the Parker spiral will be crucial for ensuring the safety of astronauts and the success of missions to the Moon, Mars, and beyond. Solar wind particles themselves are energized and accelerated by processes that occur within the Sun's corona. These processes include magnetic reconnection, a phenomenon in which magnetic field lines break and reconnect, releasing enormous amounts of energy. This energy accelerates particles to high speeds, and as these particles move outward, they are carried along by the Parker spiral. The result is that the solar wind is not a uniform, steady stream of particles but a highly dynamic and fluctuating flow that changes depending on solar activity. When solar activity is high, the solar wind becomes more intense and variable. During solar minimum, when solar activity is at its lowest, the wind slows and becomes more uniform. As the solar wind moves outward, it interacts with the interstellar medium, the gas and dust that exists between stars. The solar wind creates a boundary, known as the heliopause, where the pressure of the solar wind balances out with the pressure of the interstellar medium. The position of the heliopause is not fixed. It fluctuates based on the intensity of the solar wind and the state of the Parker spiral. When solar activity is high, the solar wind is stronger, and the heliopause moves outward. When solar activity is low, the solar wind weakens, and the heliopause moves inward. This dynamic interaction between the Sun's influence and the interstellar medium is another key area where the Parker spiral plays a vital role. Even though the Parker spiral's structure is based on processes occurring millions of miles away on the Sun, it has a direct and profound effect on the planets within our solar system. It's easy to overlook the reach of the Sun's magnetic influence because the Sun appears relatively quiet and distant from Earth. Yet, its magnetic field shapes the environment of the entire solar system. The way in which the solar wind flows, guided by the Parker spiral, impacts the magnetic fields and atmospheric conditions of planets like Mars and Jupiter, and even distant bodies like comets and asteroids. Mars, for instance, lacks a protective global magnetic field like Earth's, so its atmosphere is directly impacted by the solar wind. This exposure has led to the stripping away of a significant portion of Mars' atmosphere over billions of years, which has had major consequences for its climate and potential to support life. The study of the Parker spiral's influence on planets like Mars can provide clues about how other planets with weak magnetic fields might evolve. Moreover, this research could shed light on how habitable environments can be protected from the hostile effects of stellar winds and radiation. As we venture further into the cosmos, our understanding of the Parker spiral will continue to evolve, opening up new possibilities for space exploration and science. It is likely that future space missions will be designed to study the Sun's magnetic field and solar wind with greater precision. The Parker Solar Probe, which was launched in 2018, has already provided invaluable data about the Sun's corona and its magnetic field. As it continues its journey closer to the Sun, it will offer unprecedented insights into the dynamics of the solar wind and the role that the Parker spiral plays in shaping the heliosphere. The Parker spiral is not just a quirky feature of the Sun's behavior, but a fundamental component of our solar system's structure. It governs the movement of the solar wind, dictates the behavior of space weather, and plays a pivotal role in protecting Earth from the harsh conditions of interstellar space. It's a key player in the broader story of our solar system's dynamics, and a reminder of the intricate and interconnected nature of the cosmos. Understanding the Parker spiral allows us to make better predictions about space weather, protect our technology, and prepare for the future of space exploration. But it also serves as a gateway to understanding broader cosmic phenomena. From the behavior of other stars to the interaction of galaxies, the principles that govern the Parker spiral extend well beyond the solar system, shaping the evolution of the universe itself. Through continued research and observation, we are just beginning to uncover the true complexity of the Parker spiral. Each new discovery adds to the rich tapestry of solar and cosmic phenomena, revealing the beauty and intricacy of our Sun's magnetic field and its far-reaching influence. The Parker spiral is a testament to the Sun's dynamic nature and its role in shaping the very environment we call home. As we continue to explore the Parker spiral and its profound impact on the solar system, we begin to realize just how much we've yet to understand. The Sun, while seemingly a simple ball of fire, is far more complex and dynamic than we could ever have imagined. It is, in essence, a cosmic engine driving the forces that shape our entire solar system. The Parker spiral provides us with a unique window into the mechanics of this engine, giving us insights into everything from solar flares to the formation of planetary atmospheres. One of the key elements of the Parker spiral is the role it plays in shaping the conditions for life here on Earth. While it might seem that the Sun's influence is distant and abstract, the reality is that its effects are felt here every day, in ways both obvious and subtle. The solar wind, carried along by the twisting magnetic field of the Parker spiral, interacts with Earth's magnetosphere, creating phenomena such as auroras. These mesmerizing light displays are the result of charged particles from the solar wind colliding with Earth's atmosphere, producing light as they interact with atoms in the air. But the influence of the Parker spiral extends far beyond these visible phenomena. The solar wind plays a crucial role in regulating the Earth's space weather, which in turn affects our technology, communication systems, and even our power grids. During periods of intense solar activity, the solar wind can intensify, causing geomagnetic storms that can disrupt satellite communication, navigation systems, and even lead to power outages. This is a reminder of just how interconnected our lives are with the solar wind, and why studying the Parker spiral is so important for ensuring the stability and safety of our technological infrastructure. However, the solar wind's influence doesn't stop at Earth. As we look beyond our planet, we begin to see just how much the Parker spiral impacts the entire solar system. Take Jupiter, for example. The gas giant's massive magnetosphere is shaped and influenced by the solar wind, and the planet's auroras are a direct result of interactions between its magnetic field and the charged particles from the Sun. But Jupiter's strong magnetic field also protects the planet's moons, including the icy moon Europa, which is thought to have a subsurface ocean. Without this protective shield, Europa could be bombarded by the harsh solar wind, potentially stripping away its atmosphere and preventing the possibility of life. In fact, the entire concept of space weather, which involves the study of the Sun's influence on the solar system, is tied to the Parker spiral. By understanding how the solar wind flows and how it is shaped by the Sun's magnetic field, scientists can better predict solar flares, coronal mass ejections, CMEs, and other solar phenomena that can have significant effects on the planets and space missions. This knowledge is especially important for future manned missions to the Moon, Mars, and beyond. Astronauts traveling through the solar system will be exposed to the solar wind, and understanding its behavior is crucial for ensuring their safety. As we move forward into the age of space exploration, the Parker spiral becomes more than just an interesting phenomenon. It becomes a fundamental piece of the puzzle in understanding space weather and the broader dynamics of the solar system. The Parker Solar Probe, launched in 2018, is already providing invaluable data as it travels closer to the Sun than any spacecraft before it. The probe is gathering information about the solar wind, the Sun's magnetic field, and the behavior of the Parker spiral itself. These findings will help scientists better understand how the solar wind is accelerated, how it interacts with the interstellar medium, and how it shapes the environment of the heliosphere. The data from the Parker Solar Probe will also help refine our models of space weather and improve our ability to predict solar storms. This is especially important for protecting our infrastructure here on Earth, as well as safeguarding the technology used in space missions. Solar flares and CMEs have the potential to disrupt satellite communication, navigation systems, and even damage power grids. By understanding the Parker spiral and its role in shaping the solar wind, we can develop better strategies for mitigating the effects of space weather and protecting our technological systems. But the impact of the Parker spiral extends beyond just our technological infrastructure. It also has profound implications for our understanding of the broader universe. The Sun is just one of countless stars in the Milky Way, and many of these stars likely have their own magnetic fields and solar winds. By studying the Parker spiral and the behavior of solar winds in our own solar system, we can gain insights into the behavior of other stars and their impact on the surrounding space environment. This knowledge could help us better understand the conditions necessary for the formation of planets, the development of life, and the evolution of galaxies. In many ways, the Parker spiral serves as a microcosm of the broader forces at play in the universe. It shows us how magnetic fields, plasma, and motion combine to create patterns that govern the behavior of stars and planets. It also reminds us of the interconnectedness of the solar system and the universe at large. Just as the Sun's magnetic field shapes the solar wind and the heliosphere, so too do the magnetic fields of other stars shape the interstellar medium and the space between galaxies. Looking ahead, it's clear that the study of the Parker spiral will continue to be a key area of research for astronomers, physicists, and space scientists. With the launch of missions like the Parker Solar Probe, we are poised to unlock even more secrets about the Sun and its magnetic field. But beyond just understanding the Sun's behavior, this research will help us gain a deeper understanding of the broader forces that shape our universe. From the behavior of distant stars to the dynamics of galaxy formation, the Parker spiral is a reminder that even the smallest and most seemingly insignificant details can have far-reaching implications. The Parker spiral is far more than just a fascinating feature of the Sun's magnetic field. It is a fundamental piece of the puzzle in understanding the behavior of solar wind, space weather, and the broader dynamics of the universe. By studying the Parker spiral and its role in shaping the solar system, we can gain valuable insights into everything from the behavior of other stars to the potential for life on distant planets. As we continue to explore the cosmos, the Parker Spiral will undoubtedly remain a key focus of our research, offering new discoveries and unlocking the secrets of the Sun's magnetic influence on the solar system and beyond. As we continue to explore the Parker Spiral and its significance, it's essential to grasp the deeper implications of its interactions with the solar system and beyond. The magnetic field that generates the Parker Spiral is not just a product of the Sun's rotation, but a reflection of the complex, dynamic environment that governs the Sun's behavior and the interactions with the space around it. This field is not a static, uniform structure. Rather, it is constantly shifting and evolving in response to the solar activities that drive it. The Sun's rotation plays a key role in shaping the magnetic field that ultimately leads to the formation of the Parker Spiral. This process, which is referred to as differential rotation, happens because different parts of the Sun rotate at different speeds. The equator of the Sun rotates faster than the poles. This uneven rotation twists and stretches the Sun's magnetic field, creating a complex, swirling structure that extends far beyond the Sun's visible surface. The result of this twisting is the solar wind, which carries with it the Sun's magnetic field into the vast reaches of space. This magnetic influence is felt throughout the entire solar system and even beyond, with the solar wind extending into interstellar space, creating the heliosphere, essentially the Sun's bubble in space. As the solar wind propagates outward from the Sun, it doesn't travel in a straight line. Instead, it takes the shape of a spiral, much like a coil of wire or a corkscrew. This is the Parker Spiral. The rotation of the Sun causes the magnetic field lines to spiral outward, dragging the charged particles of the solar wind along with them. The result is a spiral structure that stretches across the entire solar system. The spiral shape is not a random or chaotic feature. Rather, it is a predictable consequence of the Sun's motion and magnetic activity. This interaction between the Sun's rotating magnetic field and the solar wind has profound consequences for the entire solar system. It shapes the way the solar wind interacts with the planets, their moons, and even distant objects like comets and asteroids. As the solar wind flows outward in a spiral, it creates a dynamic environment in which the Earth and other planets exist. The solar wind influences everything from the movement of charged particles in the magnetospheres of planets to the behavior of cosmic dust and debris. One of the more intriguing aspects of the Parker Spiral is how it influences space weather. Space weather refers to the various phenomena that occur in space as a result of solar activity. These can include solar flares, coronal mass ejections, CMEs, and solar wind disturbances. The solar wind, shaped by the Parker Spiral, plays a central role in driving space weather events, which can have significant effects on Earth and the rest of the solar system. Solar flares and CMEs are both explosive events that release vast amounts of energy and charged particles into space. These events are closely tied to the Sun's magnetic field and the twisting motion of the Parker Spiral. When there is a buildup of magnetic energy in the Sun's atmosphere, it can suddenly release, creating a burst of radiation and high-energy particles. These particles can then travel along the spiral-shaped magnetic field lines, impacting planets, moons, and spacecraft in their path. On Earth, these solar eruptions can cause geomagnetic storms, which occur when the solar wind interacts with Earth's magnetosphere. During a geomagnetic storm, the solar wind disturbs the Earth's magnetic field, causing fluctuations that can disrupt satellite communications, GPS systems, and even power grids. The effects of solar flares and CMEs are more pronounced when the solar wind is particularly strong, often occurring during periods of heightened solar activity, such as the solar maximum. Interestingly, the Parker Spiral structure also affects the way solar wind interacts with planetary magnetospheres. For instance, Earth's magnetic field acts as a protective shield against the solar wind, deflecting charged particles and preventing them from stripping away the planet's atmosphere. This is crucial for sustaining life on Earth, as the atmosphere protects us from harmful radiation. However, this protective shield is not invincible. During times of intense solar activity, the solar wind can penetrate deeper into Earth's magnetosphere, creating phenomena like geomagnetic storms. These storms can lead to a range of consequences, from auroras to disruptions in communication systems. Jupiter, with its massive magnetosphere, experiences its own interactions with the solar wind and the Parker spiral. The gas giant's magnetic field is much stronger than Earth's, and it creates an environment in which the solar wind plays a crucial role in shaping the planet's atmosphere and its moons. Jupiter's auroras, like those on Earth, are the result of charged particles from the solar wind interacting with the planet's magnetic field. However, Jupiter's magnetosphere is so large and powerful that it creates unique conditions for space weather, including intense radiation belts that can pose a threat to spacecraft passing through them. Beyond our immediate solar system, the Parker spiral provides crucial insights into the broader mechanics of star systems. As we look at other stars in the Milky Way, we see that many of them likely have similar magnetic fields and solar winds. The Parker spiral offers a way to understand how these stars might interact with their surrounding space environments. By studying the Sun's magnetic field and the structure of the solar wind, we can apply this knowledge to other stars, helping us understand their impact on the planets and the potential for life in other star systems. One of the most exciting aspects of studying the Parker spiral is the possibility that it will help us better understand the formation of planets and planetary atmospheres. The solar wind plays a critical role in shaping the conditions for life on Earth, and it may do the same on other planets. By studying how the Parker spiral influences the behavior of planetary atmospheres, we can gain insights into how planets form and how they can support life. This has profound implications for the search for exoplanets and the possibility of finding habitable worlds beyond our solar system. The Parker Solar Probe, launched in 2018, is at the forefront of this research. By traveling closer to the Sun than any spacecraft before it, the Parker Solar Probe is providing unprecedented data on the solar wind and the Sun's magnetic field. Its mission is to study the Sun's outer atmosphere, known as the corona, and gather information on the processes that drive the solar wind. The data collected by the probe is expected to answer fundamental questions about how the solar wind is accelerated and how the Sun's magnetic field is shaped. These findings will help scientists refine their understanding of the Parker spiral and its role in shaping space weather. The Parker Solar Probe's mission is groundbreaking because it will provide the most direct observations of the Sun's behavior. Previous spacecraft have studied the Sun from a much greater distance, but the Parker Solar Probe will travel closer to the Sun's surface, collecting data in ways that were previously thought impossible. One of the key goals of the mission is to understand how the solar wind is accelerated as it moves outward from the Sun. This will shed light on the dynamics of the Parker spiral and provide insights into how the solar wind behaves across the entire solar system. In addition to its work with the Parker spiral, the Parker Solar Probe is also helping to improve our understanding of space weather. By studying solar flares, CMEs, and other solar phenomena in greater detail, the probe will provide valuable data that can help scientists predict space weather events and their potential impact on Earth and other planets. This information is critical for protecting our technological infrastructure and ensuring the safety of future space missions. With the data gathered by the Parker Solar Probe, scientists will be able to make more accurate predictions about the behavior of the solar wind and its influence on the solar system. As we look toward the future, the study of the Parker spiral and the solar wind will continue to be a key focus of space research. The data collected by the Parker Solar Probe will lead to new discoveries and refine our models of space weather, helping us better understand the dynamic environment of the solar system. More importantly, this research will help us gain insights into the broader workings of the universe, offering clues about the behavior of other stars, planets, and galaxies. The Parker spiral is not just a feature of the Sun's magnetic field, it is a window into the intricate mechanics of the cosmos, offering us the chance to explore the fundamental forces that shape the universe. As we continue to explore the vast and fascinating world of the Parker spiral, it's important to reflect on the broader implications of this phenomenon in the context of astrophysics and space exploration. One of the most significant aspects of the Parker spiral is the way it shapes our understanding of space weather. The Sun's activity, as conveyed through its rotating magnetic field and the resulting solar wind, impacts not only our planet but also every object in the solar system. By delving deeper into how this process works, we can better anticipate the challenges and wonders of space exploration and understand the behaviors of other stars and solar systems. To comprehend the full scope of the Parker Spiral's importance, we must first recognize its impact on the heliosphere, the Sun's bubble of influence that extends well beyond the outer planets. The solar wind that forms this spiral structure creates a vast, ever-changing environment that shields our solar system from the harmful effects of cosmic radiation. This protective bubble is not static but constantly interacting with the interstellar medium, the gas and dust that exist in the space between star systems. The boundary of the heliosphere, called the heliopause, marks the point where the solar wind's pressure balances with the pressure of the interstellar medium. The Parker Spiral plays a key role in defining this boundary and in shaping how the solar wind interacts with interstellar space. The relationship between the Parker Spiral and the heliosphere is a dynamic one. As the Sun's magnetic field shifts and evolves, the structure of the Parker Spiral fluctuates, affecting the way the solar wind travels outward from the Sun. This, in turn, influences the heliopause location and behavior. At times of intense solar activity, such as during solar maximum, the solar wind strengthens, pushing the boundary of the heliosphere outward. During periods of reduced activity, the solar wind weakens, causing the heliopause to retreat inward. These changes in the size and shape of the heliosphere have profound implications for the protection of our solar system, as the heliosphere acts as a shield against the harmful radiation from outside our system. What makes the study of the Parker Spiral particularly fascinating is the connection between solar wind and cosmic rays. These highly energetic particles, originating from outside our solar system, can pose a serious threat to both life on Earth and spacecraft exploring the outer reaches of the solar system. By studying the behavior of the solar wind in the context of the Parker Spiral, scientists are learning how the solar wind can either protect us from or allow cosmic rays to penetrate into the solar system. Understanding this interaction is critical for ensuring the safety of astronauts who may venture into deep space, as well as for developing technologies that can shield spacecraft from harmful radiation. Moreover, the Parker Spiral holds important clues about the physical processes occurring in the Sun's corona. The solar wind, which originates in the corona, is a product of complex magnetic interactions that scientists are still working to fully understand. The magnetic field lines of the Sun, twisted and distorted by its differential rotation, play a crucial role in heating the corona to temperatures much higher than the surface of the Sun. This heating is one of the key mysteries of solar physics. How can the outer layers of the Sun be hotter than its core? The Parker Spiral may offer a clue to this puzzle, as the twisting motion of the Sun's magnetic field may contribute to this heating process. By studying the solar wind and its relationship to the Parker Spiral, researchers are gaining valuable insights into the mechanisms that drive the Sun's behavior. Understanding the Parker Spiral also leads us to better comprehend the space weather that affects not just Earth, but also the other planets in our solar system. For example, while Earth's magnetic field provides a shield against the solar wind, other planets with weaker or non-existent magnetic fields are more vulnerable to its effects. Mars, for instance, has a very weak magnetic field, which means that its atmosphere is more susceptible to being stripped away by the solar wind. In fact, scientists believe that the loss of Mars' atmosphere over billions of years is at least partially due to the action of the solar wind. Studying the Parker Spiral helps us understand how solar wind interacts with different planetary environments, and this knowledge is crucial for exploring and protecting other planets, particularly in the search for habitable worlds beyond Earth. The study of the Parker Spiral also extends to the realm of astrophysics and the search for exoplanets. As we look beyond our solar system, we encounter other stars with their own magnetic fields and solar winds. While every star is unique, many of the principles that govern the Sun's activity and the structure of the Parker Spiral can be applied to other stars. By observing other star systems and their solar winds, we can draw parallels with the Sun's behavior and gain a better understanding of how solar activity shapes the environments of exoplanets. This is particularly important in the search for potentially habitable exoplanets, as the intensity and variability of a star's solar wind can influence the habitability of planets orbiting it. The Parker Spiral thus becomes a crucial tool in the study of star systems, helping us understand the conditions that could allow life to exist on distant worlds. Looking ahead, the Parker Solar Probe continues to provide invaluable data that will refine our understanding of the Parker Spiral. As it gets closer to the Sun, the spacecraft is collecting unprecedented information about the Sun's corona, solar wind, and magnetic field. This data will help scientists unravel the mysteries of the Sun's behavior and the dynamics of the solar wind. By combining this data with models of the Parker Spiral, researchers hope to answer some of the most pressing questions in solar physics, such as how the solar wind is accelerated, how it interacts with the solar magnetic field, and how it shapes the space environment of our entire solar system. One of the most promising aspects of the Parker Solar Probe's mission is its potential to provide new insights into the nature of space weather and its effects on Earth. By studying the solar wind in greater detail, scientists hope to improve their ability to predict solar storms and geomagnetic events. This information is critical for safeguarding Earth's technological infrastructure, such as satellite communications, GPS systems, and power grids. Furthermore, understanding space weather is essential for future space exploration missions, particularly those that venture beyond Earth's protective magnetosphere. The data gathered by the Parker Solar Probe will play a central role in shaping the future of space exploration and our understanding of the solar wind and its effects. The implications of the Parker Spiral extend far beyond the study of our own solar system. As we continue to explore the cosmos, we are likely to encounter other stars with their own magnetic fields and solar winds. The principles that govern the Parker Spiral can help us make sense of the solar activity in these distant stars, and by studying the magnetic fields and solar winds of other stars, we can gain insights into the evolution of planetary systems, the potential for life beyond Earth, and the dynamics of stellar and galactic environments. The Parker Spiral is far more than just a fascinating feature of the Sun's magnetic field. It is a key to understanding the complex and interconnected processes that shape our solar system and the wider universe. From its influence on space weather and planetary atmospheres to its potential to unlock the mysteries of stellar dynamics, the Parker Spiral provides a window into the workings of the cosmos. As we continue to explore the Sun and its magnetic field, we are not only deepening our understanding of our own star, but also uncovering valuable knowledge that will shape the future of space exploration and our quest to understand the universe. The Parker Spiral's relevance does not end with its immediate connection to our Sun. Its role as a foundational concept in heliophysics and astrophysics invites further exploration into its influence on cosmic environments beyond the heliosphere. To fully appreciate the Parker Spiral's vast impact, we must examine its role as an analog for understanding stellar winds and magnetic fields in other systems. Stars throughout the galaxy exhibit a range of magnetic behaviors, from serene and stable fields to chaotic, rapidly changing ones. The knowledge gained from studying the Sun's magnetic field through the Parker Spiral provides a critical framework for interpreting these phenomena. One of the most intriguing parallels lies in young, active stars. These stars often rotate more quickly than the Sun, producing magnetic fields that are more intense and dynamic. The Parker Spiral model suggests that faster rotation rates lead to tighter and more intricate spiral patterns in the stellar wind. This could have profound implications for nearby planets. Intense magnetic activity often correlates with frequent stellar flares and bursts of high-energy particles. Such conditions may erode planetary atmospheres or create challenging environments for any potential life. By comparing these stellar systems to our own and applying what we've learned from the Parker Spiral, we can begin to piece together a more comprehensive picture of planetary habitability and atmospheric evolution. This concept is particularly significant when considering exoplanet systems within the habitable zones of their stars. The habitable zone is often referred to as the Goldilocks zone, where conditions are either too hot nor too cold for liquid water to exist. However, a planet's position within this zone is only part of the equation. The Parker Spiral teaches us that the behavior of a star's magnetic field and solar wind can dramatically alter the conditions on orbiting planets. A strong, consistent stellar wind shaped by a Parker-like spiral might protect a planet from harmful cosmic radiation, much like the heliosphere does for our solar system. Conversely, An unstable or overly aggressive stellar wind could strip a planet of its atmosphere entirely, rendering it uninhabitable despite being in the habitable zone. The Parker spiral also plays a critical role in advancing our understanding of magnetic reconnection, a process where magnetic field lines break and reconnect, releasing massive amounts of energy. This phenomenon is not limited to the Sun but is observed in stars and other astrophysical systems across the universe. The interactions between the Sun's magnetic field and the interstellar medium at the boundaries of the heliosphere are governed by similar principles. Studying these interactions offers insights into how magnetic energy shapes the universe, from star formation to galaxy dynamics. The exploration of the Parker spiral's influence extends to phenomena such as coronal mass ejections, CMEs, and their potential to create geomagnetic storms. These storms, driven by the interaction of solar wind and the Earth's magnetic field, highlight the immediate, tangible effects of the Parker spiral on our planet. The twisting structure of the magnetic field lines in the solar wind determines how CMEs propagate through space and interact with planetary environments. This has real-world implications for our technology-dependent society. Understanding how the Parker spiral guides solar wind and CMEs allows scientists to predict the severity and timing of geomagnetic storms, which can disrupt communication systems, power grids, and satellite operations. Furthermore, as humanity looks toward establishing a permanent presence on the Moon, Mars, and beyond, understanding the Parker spiral becomes even more critical. Without the protection of Earth's magnetic field, astronauts and equipment in these environments will face direct exposure to the solar wind. By studying the Parker spiral, we can better predict periods of heightened solar activity and design protective measures to shield future explorers from radiation. This knowledge is essential for creating safe habitats, sustainable life support systems, and effective communication networks in deep space. Another fascinating aspect of the Parker spiral is its potential to inform our search for extraterrestrial life. By studying how the solar wind interacts with different planetary atmospheres within our solar system, we can refine our criteria for identifying potentially habitable exoplanets. For instance, understanding how the Parker spiral affects atmospheric retention on planets like Venus and Mars helps us model similar scenarios in distant star systems. This allows researchers to assess whether a planet's atmosphere can withstand the onslaught of its host star's stellar wind over billions of years, a critical factor in determining the likelihood of life. The Parker spiral also inspires technological innovation. Instruments such as the Parker Solar Probe, which directly measures solar wind and magnetic field structures, are a testament to humanity's ingenuity in unraveling cosmic mysteries. These technologies not only deepen our understanding of the Parker spiral but also pave the way for future missions to explore the outer planets, the heliopause, and even interstellar space. The data collected from such missions enhance our ability to simulate and visualize the behavior of magnetic fields and plasma in space, opening up new avenues for research and discovery. The implications of the Parker spiral reach even further, into the realm of theoretical physics and cosmology. Magnetic fields are ubiquitous in the universe, shaping the behavior of everything from black holes to galaxy clusters. The principles underlying the Parker spiral can be applied to understand magnetic field dynamics on these much larger scales. For example, the study of magnetic fields in accretion disks around black holes or in the jets emitted by quasars might benefit from insights gained through the Parker spiral. By understanding how magnetic fields influence the motion of charged particles in space, scientists can refine models of these extreme environments. As we draw closer to fully understanding the Parker spiral, it becomes clear that this phenomenon is not just a feature of our Sun but a fundamental aspect of stellar behavior. Its study has transformed our understanding of the Sun, the solar system, and the broader cosmos. The Parker spiral is a bridge between the tangible and the theoretical, connecting the immediate effects of solar wind on our planet to the grand, universal processes that govern the behavior of stars and galaxies. In the grand tapestry of space exploration and astrophysics, the Parker spiral is a thread that weaves together many of the most profound questions about our place in the universe. It is a testament to the interconnectedness of cosmic phenomena, reminding us that even something as seemingly localized as the Sun's magnetic field has far-reaching consequences. As we continue to explore the mysteries of the Parker Spiral, we are not only unlocking the secrets of our own solar system but also laying the groundwork for understanding the cosmos as a whole. The Parker Spiral's insights are not confined to the boundaries of our solar system. It acts as a template for understanding the magnetic fields of stars scattered across the universe. Each star, regardless of its size or age, emits some form of stellar wind, a stream of charged particles propelled outward by its magnetic field and energy. While these winds may vary in intensity and composition, the fundamental principles of how magnetic fields guide these particles remain consistent. This universality of the Parker Spiral makes it a cornerstone in our quest to unravel the behaviors of stars, from quiet dwarfs to massive giants. The relationship between magnetic fields and stellar winds is central to the life cycles of stars and their surrounding environments. For example, in young star systems, the Parker Spiral-like structures can influence the distribution of protoplanetary disks, the clouds of gas and dust from which planets form. The magnetic fields can either foster planet formation by stabilizing the disk or disrupt it with intense stellar winds that blow away material. Understanding how these processes occur in other star systems is vital for piecing together the story of planetary evolution and the emergence of habitable worlds. Moreover, the Parker Spiral provides a framework for studying more extreme stars, such as pulsars and magnetars. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation, while magnetars possess some of the strongest magnetic fields in the universe. The interaction of their magnetic fields with surrounding space reveals behaviors that echo the principles seen in the Parker Spiral, albeit on far more intense scales. By studying these stellar remnants, scientists can apply knowledge of the Parker Spiral to extreme environments, bridging the gap between ordinary stars and the cosmic outliers that shape our understanding of the universe. The Parker Spiral also plays a role in the dynamics of binary star systems, where two stars orbit a common center of mass. In such systems, the interaction of the star's magnetic fields and stellar winds creates complex and sometimes chaotic environments. These interactions can lead to the transfer of mass between the stars, the creation of strong X-ray emissions, or even the ejection of material at relativistic speeds. Applying the principles of the Parker Spiral to these systems allows researchers to predict how magnetic fields influence such dramatic phenomena. Moving beyond stars, the Parker Spiral helps decode the behavior of cosmic rays, high-energy particles originating from outside the solar system. The Sun's magnetic field, shaped by the Parker Spiral, acts as a barrier that modulates the influx of these particles into the heliosphere. During periods of high solar activity, the stronger solar wind and magnetic field deflect a greater number of cosmic rays, reducing their impact on Earth. This relationship is a cornerstone of space weather science, as cosmic rays can affect everything from satellite electronics to climate systems on Earth. The Parker Spiral's reach extends to planetary magnetospheres as well. Planets with strong magnetic fields, such as Earth and Jupiter, interact with the solar wind in ways heavily influenced by the Parker Spiral's structure. The twisting magnetic field lines of the solar wind create unique patterns of interaction at the boundaries of these magnetospheres, leading to phenomena like auroras and radiation belts. Studying these interactions not only helps us understand our own planet, but also offers clues about the magnetic environments of exoplanets. For instance, magnetic fields play a crucial role in shielding planets from the harmful effects of stellar winds. Without a magnetic field, a planet's atmosphere can be gradually stripped away, as is believed to have happened to Mars. By applying the principles of the Parker Spiral to exoplanet systems, scientists can evaluate the likelihood of similar processes occurring elsewhere. This is crucial for assessing the habitability of planets orbiting other stars, especially those in close proximity to highly active stellar hosts. The Parker Spiral also influences interplanetary travel and space exploration. Spacecraft traversing the solar system must contend with the ever-present solar wind and its embedded magnetic field. Understanding the Parker Spiral structure helps mission planners anticipate the conditions spacecraft will encounter, enabling the design of more resilient systems. For example, the Parker Solar Probe, which ventures closer to the Sun than any spacecraft before, relies on models of the Parker Spiral to navigate the intense solar environment. As humanity sets its sights on interstellar travel, the lessons learned from the Parker Spiral become even more critical. The edge of the heliosphere, where the solar wind meets the interstellar medium, is a region defined by the Sun's magnetic field. The structure of the Parker Spiral influences how this boundary behaves, shaping the transition from the Sun's domain to the vast, uncharted territories of interstellar space. Missions like Voyager 1 and 2, which have crossed this boundary, provide valuable data that expand our understanding of the Parker Spiral's role at these cosmic frontiers. The Parker Spiral also holds implications for the study of galactic magnetic fields. On a much larger scale, galaxies possess magnetic fields that influence the motion of stars, gas, and cosmic rays. While the mechanisms driving these fields differ from those in stellar systems, the principles of magnetic field dynamics share similarities with the Parker Spiral. By studying the Sun's magnetic field, scientists gain insights into the behavior of these vast, enigmatic structures, contributing to a deeper understanding of galaxy formation and evolution. Perhaps one of the most exciting aspects of the Parker Spiral is its potential to reveal hidden patterns and connections in the universe. The intricate dance of magnetic fields, plasma, and particles that defines the Parker Spiral echoes similar dynamics observed in other astrophysical systems. From the swirling accretion disks around black holes to the vast filaments of gas connecting galaxies, the principles underlying the Parker Spiral offer a window into the interconnected nature of the cosmos. The Parker Spiral is a reminder of the profound influence of seemingly simple principles on complex systems. It demonstrates how the rotation of a star and the behavior of magnetic fields can shape entire regions of space, influencing everything from the behavior of planetary atmospheres to the trajectories of interstellar particles. As our understanding of the Parker Spiral deepens, it not only enhances our knowledge of the Sun but also provides a lens through which we can view the broader universe. This enduring relevance of the Parker Spiral underscores its importance as a cornerstone of modern astrophysics. Its study represents the intersection of observation, theory, and technology, showcasing humanity's ability to unravel the mysteries of the cosmos. From the smallest charged particles to the vast expanse of interstellar space, the Parker Spiral is a testament to the beauty and complexity of the universe. The Parker Spiral's significance isn't confined to our immediate understanding of solar phenomena. It holds the key to answering profound questions about the nature of space and time. The spiral's structure reflects an intricate interplay between the Sun's rotation, its magnetic field, and the charged particles it ejects. This phenomenon doesn't just inform us about the Sun but also raises fundamental questions about how magnetic fields behave in dynamic systems throughout the cosmos. A key feature of the Parker Spiral is its ability to adapt and evolve in response to solar activity. During periods of high solar activity, such as solar maximum, the Sun's magnetic field becomes more complex, with increased twists and irregularities. These changes ripple outward through the solar wind, distorting the spiral and creating regions of heightened turbulence. These turbulent zones are of particular interest to scientists because they provide a natural laboratory for studying plasma physics, a field critical to understanding the behavior of charged particles in both terrestrial and cosmic environments. One of the most puzzling aspects of the Parker Spiral is how it interacts with the heliosphere, the bubble-like region of space dominated by the solar wind. The heliosphere acts as a shield, protecting the planets from the interstellar medium, a sparse collection of gas, dust, and cosmic rays that fills the space between stars. The boundary of the heliosphere, known as the heliopause, marks the point where the pressure of the solar wind balances the incoming forces from interstellar space. The Parker Spiral plays a critical role in shaping this boundary, influencing its structure and dynamics. As the solar wind flows outward, carrying the Parker Spiral with it, it eventually slows down and becomes compressed when it encounters the interstellar medium. This region, called the termination shock, is a zone of intense interest. Here, the behavior of the Parker Spiral changes dramatically, with its magnetic field lines becoming more chaotic. The study of this region has been significantly advanced by spacecraft like the Voyagers, which have crossed the termination shock and entered interstellar space. Their data provide a glimpse into how the Parker Spiral transitions from the Sun's domain to the broader galaxy. This transition zone also has implications for the study of cosmic rays. The Parker spiral's magnetic field acts as a modulator for these high-energy particles, deflecting some and allowing others to pass through. The intensity and distribution of cosmic rays within the heliosphere depend on the structure of the Parker spiral, which varies with the solar cycle. During solar maximum, when the magnetic field is more complex, fewer cosmic rays penetrate the heliosphere, offering a form of natural shielding. Understanding this process is crucial for protecting astronauts and spacecraft from the harmful effects of cosmic radiation. The Parker spiral also serves as a bridge between our understanding of the Sun and the behavior of other stellar systems. Stars with magnetic fields and stellar winds similar to the Sun's are likely to produce their own versions of the Parker spiral. These stellar spirals could influence the habitability of planets orbiting these stars by shaping their magnetic environments and shielding them from cosmic radiation. Studying the Parker spiral thus provides a framework for evaluating the conditions necessary for life in other parts of the galaxy. Moreover, the Parker spiral offers a unique perspective on the role of magnetic fields in shaping cosmic structures. From the smallest scales, such as planetary magnetospheres, to the largest, like galaxy clusters, magnetic fields play a unifying role in the universe. The principles governing the Parker spiral can be applied to understand these diverse systems, offering insights into phenomena ranging from the formation of stars to the behavior of black holes. One of the most exciting applications of the Parker spiral is in the field of space exploration. As humanity ventures farther from Earth, understanding the dynamics of the solar wind and its magnetic field becomes increasingly important. Spacecraft must navigate the Parker spiral's complex structure, which can affect their trajectories and communication systems. Missions like the Parker Solar Probe and the European Space Agency's Solar Orbiter are designed to probe the Parker spiral up close, providing unprecedented data that will refine our models and enhance our ability to predict space weather. Space weather, driven by the Sun's activity, is a direct manifestation of the Parker spiral's influence. Solar flares and coronal mass ejections, which are intense bursts of energy and particles from the Sun, propagate along the spiral's magnetic field lines. When these events interact with Earth's magnetosphere, they can produce geomagnetic storms that disrupt power grids, satellite operations, and communication networks. By studying the Parker spiral, scientists aim to improve their ability to forecast these events, reducing their impact on modern technology. The Parker spiral also has implications for understanding the origins of the Sun's magnetic field itself. The Sun's magnetic field is generated by a process known as the solar dynamo, which involves the movement of conductive plasma within its interior. The rotation of the Sun, combined with convection currents, creates a complex magnetic field that extends into space. The Parker spiral is a visible manifestation of this field, offering clues about the underlying processes that drive the solar dynamo. Understanding these processes is essential for unraveling the mysteries of magnetic fields in other stars and even planets. In addition to its scientific significance, the Parker spiral serves as a source of inspiration and wonder. Its elegant structure, shaped by the interplay of fundamental forces, embodies the beauty and complexity of the universe. The Parker spiral reminds us that even the most intricate phenomena can arise from simple principles, a theme that resonates throughout the natural world. It challenges us to look beyond the surface and seek deeper connections, encouraging a sense of curiosity and exploration that drives scientific discovery. As we continue to study the Parker spiral, we uncover new layers of understanding about our Sun, our solar system, and the broader universe. It stands as a testament to the power of human ingenuity and the enduring quest for knowledge. By unraveling the mysteries of the Parker spiral, we not only deepen our understanding of the cosmos but also gain insights into the forces that shape our own existence. The Parker spiral is more than just a feature of the solar wind, it is a window into the interconnectedness of the universe. It links the Sun to the planets, the solar system to the galaxy, and humanity to the stars. In its intricate curves and spirals, it holds the keys to unlocking the secrets of magnetic fields, stellar dynamics, and cosmic evolution. The study of the Parker spiral is a journey that continues to reveal the wonders of the universe, reminding us that even the simplest patterns can hold the deepest truths. The Parker spiral extends its influence far beyond our solar system, embodying the universal principles of magnetic field dynamics. Its far-reaching impact on space environments raises fascinating questions about the fundamental laws governing our universe. Magnetic fields, as showcased by the Parker spiral, are essential to understanding the behavior of charged particles, the evolution of celestial bodies, and even the potential for sustaining life. The idea that the Parker spiral might have analogues across the galaxy is particularly intriguing. As we study exoplanets and their host stars, we're discovering that many stars exhibit stellar winds and magnetic fields that could form spiral-like patterns similar to those in our solar system. These spirals may shape the space weather in these systems, influencing the habitability of exoplanets by shielding them from harmful cosmic rays or exposing them to intense radiation. By understanding the Parker spiral, we gain tools for interpreting these distant phenomena and assessing the potential for life beyond Earth. One of the most captivating aspects of the Parker spiral is how it exemplifies the dynamic and ever-changing nature of space. Unlike static magnetic fields, the spiral reflects the continuous motion of the Sun's rotation and its pulsating activity cycles. This dynamism reminds us that space is not a vacuum devoid of activity, but a bustling environment filled with energy, movement, and interaction. The Sun's magnetic field lines are frozen into the plasma of the solar wind due to the high conductivity of the plasma. As the Sun rotates, these magnetic field lines are dragged outward, forming the spiral pattern that defines the Parker spiral. This process, while conceptually simple, results in a structure of incredible complexity and beauty. The spiral's curves and arcs are shaped by the Sun's rotation speed, the velocity of the solar wind, and the Sun's magnetic field strength, all of which vary over time. Solar activity plays a significant role in modulating the Parker spiral. During periods of solar maximum, the Sun's magnetic field becomes more chaotic, with frequent reversals and intricate twists. These changes propagate outward, altering the shape and structure of the Parker spiral. The increased turbulence during these periods can enhance the acceleration of particles, contributing to phenomena like solar energetic particle events, which pose risks to astronauts and spacecraft. The interaction of the Parker spiral with planetary magnetic fields adds another layer of complexity to this phenomenon. Planets with strong magnetic fields, like Earth, create bow shocks where the solar wind is abruptly slowed and redirected. These bow shocks can distort the Parker spiral's magnetic field lines, leading to complex interactions that influence a planet's magnetosphere and ionosphere. For example, during geomagnetic storms triggered by solar wind disturbances, the Parker spiral's magnetic field can connect with Earth's magnetic field, transferring energy and driving spectacular auroras. The Parker spiral's role in shaping the heliosphere also has profound implications for our understanding of the solar system's boundary. The heliosphere is not a perfect sphere but an elongated, teardrop-shaped structure influenced by the motion of the solar system through the interstellar medium. The Parker spiral's magnetic field extends outward to the edges of the heliosphere, interacting with the interstellar medium and influencing the structure of the heliopause. Data from the Voyager spacecraft have provided unprecedented insights into these interactions. As these spacecraft crossed the termination shock and entered the outer heliosphere, they observed changes in the solar wind's speed, density, and magnetic field strength, all influenced by the Parker spiral. These observations reveal a region of space where the orderly structure of the Parker spiral gives way to turbulence and chaos, highlighting the complex interplay between the solar wind and the interstellar medium. The study of the Parker spiral also informs our understanding of astrophysical phenomena beyond the solar system. Many of the processes that shape the Parker spiral are thought to occur in other astrophysical contexts, such as the accretion disks of black holes, the winds of massive stars, and the magnetospheres of exoplanets. By studying the Parker spiral, we develop models and theories that can be applied to these distant systems, bridging the gap between our solar system and the broader universe. For example, the concept of a rotating magnetic field shaping a plasma flow is relevant to the study of pulsars, which are rapidly rotating neutron stars with intense magnetic fields. These objects emit beams of electromagnetic radiation and accelerate particles to nearly the speed of light, creating phenomena that are in some ways analogous to the solar wind and the Parker spiral. By understanding the mechanisms behind the Parker spiral, scientists can gain insights into the processes that drive these exotic objects. The Parker spiral also has implications for understanding the Sun's long-term evolution and its impact on the solar system. Over billions of years, the Sun's rotation has slowed due to the loss of angular momentum through the solar wind. This slowdown has likely influenced the structure of the Parker spiral and its interactions with the solar system. By studying the Parker spiral, we can infer the Sun's past behavior and its future trajectory, shedding light on how the solar wind and its magnetic field have shaped the solar system over geological timescales. Moreover, the Parker spiral serves as a reminder of the interconnectedness of all things in the universe. Its structure links the Sun to the farthest reaches of the heliosphere, connecting the planets, comets, and interstellar medium in a vast, dynamic system. This interconnectedness highlights the importance of studying the Sun and its magnetic field not only to understand our immediate environment, but also to gain insights into the broader cosmos. In recent years, advances in technology have allowed scientists to study the Parker spiral with unprecedented detail. Instruments on spacecraft like the Parker Solar Probe are providing high-resolution measurements of the solar wind's speed, density, temperature, and magnetic field. These data are helping scientists refine their models of the Parker spiral and uncover new phenomena, such as small-scale magnetic structures and wave-like disturbances that propagate through the solar wind. As we continue to explore the Parker spiral, we are reminded of the Sun's profound influence on our solar system and beyond. The Parker spiral is not just a feature of the solar wind, it is a testament to the dynamic and interconnected nature of the universe. Its study offers a glimpse into the forces that shape our world and inspires a sense of wonder and curiosity about the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.